Okay, guys, one last example of Hill cipher. So Hill cipher depends on matrix operations, and the matrix operations, you always need the matrix that encrypts the data and the inverse matrix to decrypt the data. Encryption and decryption operations are exactly the same. Multiply the data into the matrix, either the key matrix or the inverse matrix. So we go straight for an example. Maybe we should work out by hand, an example by hand. Let's have a quick look at the operation. The Hill cipher, in this encryption, you'll need to make all the values that are used a modular value, depending on the modulo we're using. In our example, we're using modulo 26. It can be of any type modulo, of any size, depending on what the alphabet is and what you want to include in the alphabet. You can include other characters, not necessarily the alphabet characters, but any other characters like commas, equal, multiply, or any other. And also the numerical values can be included as characters as well and given a value. So the modulo can increase in size. You can have capital and small letters as well. But we'll keep it small at 26. Then the next operation or the next part is to calculate make sure you have the matrix for encryption and work out what the inverse of that matrix is if you need to do the decryption operation. And in order to work out the inverse of the matrix, you need the determinant of that matrix and then work out the adjuvant of the matrix and work out the actual inverse and use the inverse for decrypting. Now, the quick idea is that if the determinant of the matrix is not one of these numbers, is not an odd number between 1 and the modulo, and in this case also not to include number 13, then it's one of those numbers, then the matrix will have an inverse. And if it's not, then there'll be no inverse for that matrix. Well, here's the example we're taking. We use 2 by 2 matrix to encrypt or decrypt information. And if this is the original matrix, then we need to convert the numbers into modulo 26. So any number that's above 25 or below 0, it's to be modded to the 26 modulo. And the operation goes from there. So here's an example of the matrix to be used. If you want to use this matrix for encryption, then you need to convert it into modulo 26 matrix. And to use it for decryption, then we need to generate the inverse of that matrix. So let's first convert this into modulo 26. I mean, all numbers are converted, divided by 26, and the remainder is placed there. So if the numbers are in any number between 0 and 26, they will not change. If they are any bigger, then you lose 26 for each one of them. Or you know the mod operation, divide it and take the remainder. So 25 divided by 26 is 0, and the remainder is 5, and that's what remains there. And that's the modulo of 26. Now, if the number was, for example, 28, 28 divided by 26 is 1, and the remainder is 2. And that's what the mod is, 2. Now you need the negative numbers to mod a negative number by, say, 26. It's like you count backward in the numerical, from 0 going into the negative value, or you keep adding the value plus 26 to the negative number until you have finally a positive number between 0 and 20 and less than 26. And that will be the outcome. So in this particular case, it's easier to add minus 29 plus 26. That gives us plus 17, and that's the modulo. It's one way of calculating. There are a few different ideas of how to do it. Find out the technique that works for you. You're allowed to use calculators in the exam, so find a calculator that has the modulo function, the mod function. I recommend it because in an exam, in a pressure situation, you might get the wrong number, and that will work out through the rest of the example with wrong results. So that's the first thing you do. If you're given, and it's almost a guaranteed exam question, is to encrypt or decrypt using Hill cipher. Make sure you know how to use it. So first thing you need to do with the matrix you have is to convert it into a mod 26 matrix, and then find the determinant for that matrix. And the determinant, we looked at a number of ways. It's not going to be more than 3 by 3 on the outside. We'll most likely will be using the 2 by 2. The main idea, the point is that you know how it works. We don't want you to maybe spend an hour working at it if it's exactly the same idea once you know how to do it. But most likely it's going to be 2 by 2, but you should know how to calculate the determinant for 3 by 3. We had maybe 2 or 3 ways of doing it, but you can revise them. So the determinant for 2 by 2 matrix is to multiply those two numbers minus the multiplication of those two numbers, the product of those two numbers. So it's 5 times 3 minus 17 times 8, and that's whatever. The outcome here is minus 121. You need to mod that. Minus 121 modded by 26. This way you start, if you're at an exam situation, a short of time, you need to it's good to have the calculator. It's divided by 26, so we keep adding 26 until you have a positive number. And that positive number less than 26, between 0 and 26, that number would be 9. So that's what we got here. The determinant of this matrix is 9. That's those two multiplied together minus those two multiplied together. That gives us a number. If it's less than 26, that's fine. If it's a positive number less than 26, then you finish, you got the determinant. If not, you have to mod it. If it's above 25 or below 0, then you must mod it to 26, and that gives us 9. And if it had given us 10 instead of 9, that's okay. Then it means this matrix may or may not have an inverse. If it's 9, then it will have an inverse. If it's 10, if that determinant is 10, then that's it. That matrix is no good to be used for encryption because you won't be able to decrypt the information. There is no inverse for that matrix. So this number immediately will tell you there is an inverse for this matrix or not. If it's a number, an odd number between 1 and 25, excluding number 13, then it's okay. We'll go with it. So that's the first thing. So we have now a matrix and its determinant. We need to find the inverse matrix. and the inverse determinant. We need to get the inverse determinant to work the other way. Instead of having the matrix work out the determinant, now we need the inverse determinant to work out the inverse matrix. So the inverse determinant of 9 is based on this one here. It's actually 3. It's the number that 9, you multiply, whatever number you multiply it into 9 and mod it by 26 if the remainder is 1. So that number is considered relative prime to one another. So this is the actual, if you don't remember, these just start with the numbers from 1 to 25. Multiply the number into 9, multiply by 26, and see if the result is 1. If the result is 1, then that's the inverse. That's the modular inverse. It's only as far as the modulo 26, they are inverse. Otherwise, they may not be. They should be primes. They should be prime numbers, even though we know 9 is not a prime number. It's only relative to 26, it is a prime. It doesn't have a common denominator or divider between it and 26. So, and we also, so we got the inverse of the determinant, which is 3. Now we need to find out the inverse matrix. We need to get the adjective of this matrix. That will generate the inverse of this matrix. How do we kind of inverse it? We swap those two numbers and change the sign of those two numbers. And that gives us the adjective matrix that now we can multiply it into the inverse determinant, and that will give us the inverse matrix. So that's something you need to create, find out. Now, that's the adjective matrix. So we have an original matrix. We created the adjective. The original matrix had a determinant. This is the inverse of that determinant. Now, if we multiply that into that, we get, hopefully, the inverse matrix. Now, it's a result for multiplying that determinant into the adjective of the matrix. Now, this is the inverse matrix, but it won't work with us on the modulo 26. So we need to convert it into modulo 26 matrix. And that's any number that's above 25 or 26, or any number that's below 0, we need to change it. And that's modded by 26. So this is exactly the same as this one, mod 26. So the 9 and the 15, they remain unchanged, but minus 24 mod 26 gives us plus 2, and minus 51 plus 20, mod 26. That's if you add 26 to it and another 26, you get a 1 positive. And this is where I always make mistakes as well. And I look at it and I say, oh, it's minus 52, that's a 0, when it's wrong. Because I keep thinking 52 divided by 26, it's 2, so it's and the remainder is 0, but that's not how it works. Be careful, you need to practice it a couple of times just to make sure you know how to do it. It's simple and easy, but it can mislead you quite easily. Now, so we got the inverse matrix. That's our inverse matrix. And it's good in an exam to make sure that, ensure that that is the inverse of the original matrix. And how do you check it? You multiply, if that's your original matrix, this one here, therefore, we'll work with both, but we'll work with the mod solely, the mod 26s. That's the original matrix that we can use for encryption. That's the inverse that we can use for decryption, or vice versa. But how do we know these two are the inverse of one another? Did we do it right? We'll multiply them into one another, and we should have the result of the identity matrix. Know what the identity matrix look like? You do. Yeah, that's all. Thank you. I just want to make sure you do it. All right. So if you multiply those two together, you multiply, you know how to multiply matrices? This row into this column and then that column to give you this value and then that value. And then you go down to the next row Now go into this column and that column, they give you those two values. So 5 times 9 is 45, plus 8, 53. So that's the number there. And then 5 and 8 multiply into 2 and 15, so 5 times 2 is 10, and 8 times 15 is 120, so that's a total of 130. And then mod them by 26, mod this by 26. So the 53 modded by 26 is 26, 26 is 52, and 1 remains, so that's the remainder. And 130 modded by 26 is possibly 6 times, and the remainder is 0. And that's it. We got the identity matrix. And that means at least we have the exact inverse. So these two are the inverse of one another. Now, let's encrypt and decrypt some values using those two matrices. So maybe if you could encrypt and decrypt values just to make sure that really this is the difficult part is done, finding the inverse. Now let's encrypt and decrypt. What I'd like you to do is maybe encrypt the following message for me, please. Maybe GCD, that's a Griffith College, Dublin, Ireland. And you encrypt this message using Hill cipher. Use Hill cipher, and you can maybe, just keep it small, just 4 characters. Okay, who doesn't have a piece of paper and a pencil? Oh, you have a friend who has lots of paper, right? Oh, you have a bag. Oh. There you are. Okay. Oh, fantastic. So you're going to do it electronically. Okay, you can start a word in any file that you can use for editor. Are you carrying a piece of paper? Okay, do you know how to do this? You need the grid for the alphabet. You know the A, B, C, D, all the way to X, Y, Z. 0, 1, 2, 3, 4. I go as far as the G, H, E, F, G, H, I. 6, 7, 8, all the way to 23, 24, 25. You should get this grid. I'll get you the grid if it's there. No, that's not it. I don't know. I don't have the grid. No, there it is. There's a grid. Forget about everything else, but just showing you what the grid is like. So first you convert, what's G? Convert these into numerical values. G is 6. And C is 2, and so on. DI, which is 3 and 8. So that's really what you want to encrypt, 6238. How do you encrypt those? You take the matrix, encryption matrix. Where is the encryption? Is this it? Yeah. Oh, this is the encryption matrix. Use this encryption matrix to encrypt the message. So the encryption matrix is 5, 8, 17, 3, multiplied into. So you take your message, in this case, this is 2 by 2 matrix, then you take your message 2 characters at a time. If it's 4 by 4 matrix, you can take 4 messages at a time. In fact, when they do it in real life, in programming, they do 50 by 50 matrix, or 100 by 100. And as you can see, it takes a lot of processing power. a lot of time to work on computer, but we'll use 2 by 2 matrix. So you take the first, the encryption matrix and multiply it into the first two numbers, which is 6 and 2, which are, I just write them here, they are G and C, but you don't have to write them, it's just G is 6 and C is 2. And multiply, get us the value, what the value is. It will be two numbers, one on top of the other, and then convert them into characters. So find out what's the number there and what's the number there.
We can use any matrix for.
Don't forget here, mod 26, and that equals whatever the final value is.
I was saying that we can use any matrix on that place.
Oh, well, yeah. Let's, for now, using the G is represented by 6 and the C is represented by 2.
I'm talking about that one, 5, 8, 17. If we can use any other matrix on that place, but for that we need to check that its inverse is like.
Oh, you've already checked it. There. This is the inverse. We've already done that. So, okay, if you're given the example, I will have an example later on. Here's already encrypted using this matrix. Can you decrypt it? First, you have to find out the inverse matrix and prove that it is, and then multiply the inverse. But let's just do it one step at a time. Yeah. You got the characters that will encrypt GCDI. Yeah, what character is that? Okay, see, this should be mod 26. See, I've added mod 26, so you need to mod these by 26. Multiply 26, please. Maybe it's a good idea to have a calculator on your laptop. You know, it comes usually with the operating system. And see if there? So I want you to encrypt the GCDI. G is 6 and C is 2. And to encrypt the DI is 3 and 8, right? 3 is D and I is 8. So it also needs to be multiplied into the encryption matrix. So the encryption matrix multiplied into the next two characters of your message, and this will generate 2 more cipher characters. Anybody got me the cipher characters yet?
I got 25.
And model those 2 numbers by 26. Sure. If anybody doesn't know how it's done, put your hand up now. Once you learn it now, then you'll never forget. Yeah. You have that, you multiply this row into this column, and then get you one value. Then bottom row into the next column. So this is 17 times 6 plus. Yeah. What, 26? And then what equals, and then what each one of them by 26. Yeah. What's that? 20. What number is 20? What character? Okay, all right. We need to confirm that. Okay, work out the next one. How did you work it out? Okay, multiply that by that and read up this number. That's 46. Yeah. Yeah, it looks good. Now, do the same thing for the next 2 characters. That's D and I. Let me first get my glasses because I'm seeing things different now. I have a pair of glasses, yeah. And sticking this one here because I'm counting the sets. No, let's go through this. How did you do it? I don't think it. So it's those two numbers. Anybody having any issue? Okay, somebody else got the U. I don't know what the E, so I'll spell this for a second. What country again? Yeah. Okay. It's confirmed by somebody else. Good. Okay, what's 20 and 4? You need to look at the grid again. I'll bring you back to the grid. Okay, everybody got the. There it is. Let me get a copy of this. Yeah, that's better. Oh, I can hear. Okay, so if you got 20, it's U, the character U, and what did we get here, the first one? 20 and U, 20 and 6, is it? 20 and 4, which is U and D. E, thank you. This one?
122.
Which is B and X, is it? Good. That's
123.
6 and 2. So 5 times 2 is 16, 30 and 16 is 46. 46 multiplied. What will that give us? Hey guys, so this one is 5 times 6 is 30. I'll just write it here. 8 times 2 is 16 plus 16, so it's 46. 46 divided by, multiplied by 26 leaves us with 20. Okay, so what are the characters? To cipher it, that's U, E, what's all up here?
X.
B and A, is it?
X.
Now, let's decrypt this. Okay, the original question, guys, is going to be like this, 5, 8, 7. 5, 8, 17, 3. This is how most likely your questions are going to be like this. Okay? Just stay with me for a second. The question is, you're given a message that's an encrypted message and says, can you decrypt it using Hill cipher? And this message was encrypted using this matrix. This is the key matrix. That's the kind of questions you get. You get the matrix and the ciphered message. Now you're asked to decipher it. In order to decipher it, you must first work out the inverse matrix. We've already worked out the inverse for this one. But the next example we're going to get, you'll have to work out the inverse. But for now, just decipher this message. We know what the inverse message is. So there it is, just decipher it. Decipher this, please. Just to make sure. Yeah. Can you decipher UEBX? It was ciphered using this matrix, but now we have the inverse matrix. So use the inverse matrix to reverse it. See how would it work? Would it be able to divert? So first you have to work out what the numerical value is. So UE is 20 and 4. So you'll have to convert, this is 20 and that's 4, and B is 1 and X is 23. And if the matrix is 2 by 2, then you're going to take 2 characters at a time. If the matrix is 3 by 3, you'll have to multiply it into 3 characters each time. Now, okay, you will have to work out what the inverse of this matrix is, but for now we have it. So that's the 9, 2, 1, 15. 9, 2, 1, 15. This is the inverse matrix that's going to be used to decipher the message. And you'll have to multiply it into the numerical value for the ciphered message. So multiply it into 20.4 here and mod by 26. Whatever result you get is going to be modded by 26. So just do it for the first 2 characters, just quick so we won't waste too much time. Can you decipher those 2 characters? UE using this inverse matrix, this matrix that's to be used for deciphering. The same technique, you multiply 2 matrices. Well, this row into this column, and then this row into this column. You get 2 different numbers here. Mod them by 20, and they should be, right?
Yes.
Which is GC. So this result here should be something like 6 and 2, is it?
Yes.
Which is the letter G. Griffith College. Make sure it works for you. If it works once, it will work all the time. If it doesn't work, you have it until you know how it works. It's simple enough once you do it, but if you don't do it, Good. Okay, does it show on the Zoom screen? This one here. Okay, now, here's a full example. Work out this example now in the next 10 minutes. So, this is the message. This is a ciphered message. Whatever the message is, YAM. And this was the original matrix that was used to encrypt the message. So that's our key matrix. We took a message, we used this matrix to encrypt it. It generated this ciphered message. Can you please decipher this message? So here are the steps that you need to do to decipher the message. First, you need the inverse of that matrix. To get the inverse of the matrix, you need the determinant of this matrix and work out the determinant of the other matrix.
There should be 126, right?
Calculate 126. Yeah, I just removed the 6. Just to check you out that you're okay. Okay, so calculate the determinant, multiply by 26. Check the inverse of that determinant, apply it to the adjacent matrix of this one, and then you'll have the inverse matrix. Then multiply the inverse matrix into that ciphered message, you get the original message. If you do this, then you'll have no problem with Hill cipher. If you can't do it today, you'll need to go over. And I'm here to show you. If you have a problem, just let me know. How to do this. And you will not have this grid. You'll have to come up with it yourself. The 0 to 25 grid. You'll not have the inverse of the determinant either. And then 22. And then 3, 4. Okay, so the multiplication operation is simple there. It's 9 times 3. 9 times 3 is 27. Divided by 26 is 1, the remainder is 1. If the remainder is 1, then it's perfect. That's what we're looking for. If the remainder is not 1, then don't try number 3. Yeah, 1, 3, 5, 7, 9. Or it's already there. Okay, guys, some people don't know how to, when you get the determinant of this one, how do you get the inverse? This is the rule for. Okay, let's say, for example, you get the determinant here is 5. For example, 5. This is the determinant of this one. We need to find the inverse determinant of 5. You say 5 times 1 mod 26. 5 times 3, 5 times 5, 5 times 7, all the odd numbers until up all the way to 5 times 23. So 5 times 5 is 5, mod 26 equals 5. That's no good. We're looking for equals 1. If it equals the remainder is 1, that's the one we're looking for. 5 times 3 is 15. Mod 26, still 15. So that's no good. 5 times 5 is 25. Mod 26, it's, what's 25 mod 26? 25. That's no good. Until you find the remainder is 1. And that's the actual inverse of that number. They have to be, those two numbers are relatively primes, that the two of them with the number 26. If you multiply one model by 26, they should have a remainder of 1. I already have that result for you in a small table, if you like, but it's up to you whether you want to use that table. I can't remember where it is now. It's very few of them. Anybody worked out what the determinant for this one is yet? Yes. Good. Have you worked out the inverse determinant? Yes. Okay, have you got the inverse matrix? Okay, then. So you got the two matrices. The determinant is those two minus those two. Oh, that's the edge. Oh, okay, you've already know that. So you worked out what the determinant is. Okay. Minus it, you have to convert. It has to be a number between 1 and 25. It's not 1. So you have to mod it first and then start working on that. And it's not 1 over, it's the actual determinant times the adjective, not 1 over it. It's not 1 over the determinant, it's the inverse determinant multiplied into the matrix. First work out the determinant. You got the determinant minus 17, you have to convert that first into a line. Okay. Now the determinant is 9. Now we want the inverse of this determinant. Which is 3. 7 mod 26 is 1. That's good. Yeah, not 1 over 3. And that's the adjective. What's the determinant?
Yeah.
Now we want it to 26 to
Minus 17.
yeah. Actual determinant. The determinant has to be a positive number.
Yes.
All right. All right. Here are the steps actually to do it, and you need to be able to do that. Right. That's why we're doing it now. Great. So the first one is find out the determinant for this matrix. This matrix is the one that was used to encrypt the messages. So we want to find out first the determinant of this matrix. The determinant for 2 by 2 matrix is multiply those two of the diagonals 4 times 1 minus the other two numbers. The product 4 times 1 minus 3 times 7. So it's going to be 4 minus 21. And that gives us the actual determinant, which is minus 17. Where did you get that far? I don't know what what's the adjective? And then start multiplying. That's your following. Three. Okay, sorry. Correct, yeah. And then multiply.
5,000.
3,000. 5,000.
Now, in order, see the idea we want to work out what's the inverse of that matrix. What's the inverse of whenever we do Hill cipher, all numbers have to be more than 26. Any number bigger than 26 or smaller than 0, we have to multiply. Decipher that. Now, this is the determinant for that matrix. This and I have a table there, or to follow this method, whichever one. There's a table that, so for example, 9, we multiply 9 times 1, 9 times 3, 9 times 5, 9 times 7, and each time you multiply 26 until you have a remainder of 1. Whichever one, if it's remainder of 1, then that's our. Say, for example, I know it's 3, so it's 9 times 3 is 27. Mod 26, that's divided by 26 is 1, and the remainder is 1, and that's it. And there's only one of them between 1 and 25, it has to be only an odd number, except 13. So in this case, it's the inverse of 9 is going to be, so for the inverse matrix, its determinant is going to be. Right, now, the next step, yeah? Yeah, CCNA. Oh yeah, somebody has got something. So the inverse of this, in order to generate the inverse of any matrix, you need the inverse determinant, but also you need something called the adjugate of this matrix. You inverse this matrix and the adjugate is you swap these two numbers and change the sign of those two numbers. And that's the adjugate. Now multiply it with the new inverse matrix and now we get the adjugate of this matrix. Swap 4 and 1 and change the sign. Now, once you get the inverse matrix, check that it is the correct one. You may get the wrong one, and you start using it and you don't get the final. So, and by ensuring that the two matrices are the inverse of one another, multiplied with one another, make sure there is one. The there's something wrong with the inverse matrix. Okay, what's the inverse matrix?
Multiply the inverse model. So inverse model find it's
How did you start? First you get the determinant for this one. Did you get the determinant for this one? It's 9, right? Calculate the determinant. So just here, number 1, the result is 9. Right, find out the inverse modular determinant. Oh, if you didn't get 9. Plus 26. That's minus 16 minus 7 is 9. 1 minus 1.
उसको वैसे करेंगे
You confirm what you got is the actual inverse. That's good. Hey guys, everybody is almost there. Okay, so remember the steps here. First, we calculated the determinant for this matrix, and it's 9. And then we inversed the determinant. 2 ways to do it. But ultimately, it's any number that you multiply into that determinant multiplied by 26. If the remainder is 1, then that's the one we want. So it's 3. Now, so this is the determinant of the original matrix. This is more or less the determinant of the inverse matrix. Now, how do we create the matrix itself? We take the original matrix, create the adjecate. The adjecate matrix is just reversing those two diagonals. 4 and 1 becomes 1 and 4, and then change the sign of those two numbers so it's -7 and -3. And multiply them into the new determinant, which is 3. And that gives us 3 times 1 is 3. 3 times 7 is -21, 3 times 4 is 12, and 3 times -3 is -9. And this is the inverse matrix. But it's not the determinant 26 inverse matrix. To make sure it is that it won't work in our deciphering unless we use the 26 determinant. And in order to do that, you change it into the mod. So you multiply 26, and that's 3 times. Every number is divided by 26, and that generates a remainder, which is most of you have created. What's the new matrix, guys? Anybody has the new matrix? The inverse matrix? What is it?
3, 5, 17, 12.
So this is the inverse matrix, and this is the original matrix. We don't know if it is. Don't go any further unless you confirm that this is the correct inverse. Because you could waste your time in an exam thinking you got the correct inverse. So to make sure they are the inverse of one another, you multiply them, and you should get 1, 1, the identity matrix. If you get the identity matrix, then that's a proof. Sometimes you get a question, can you find the inverse and prove that it is the right inverse? And that's the proof, is multiply them into one another. But now once you're happy, this is the matrix that I use to encrypt a message, and we got this ciphered message. Now, to work this ciphered message back, we need to get this inverse matrix and multiply it into it. So now we're going to use this matrix 3, 5, 17, 12, which is the inverse. This matrix was used, the original matrix was used to encrypt, and this inverse matrix is used to decrypt. And to decrypt the message we're going to decrypt is WIAN. And we said if you have a 2 by 2 matrix, then you multiply it into the WI. But of course, it's not the characters, and we multiply the next 2 characters into same matrix is multiplied into the next 2 characters, which is WI, and the next one is AN. But remember, we need to convert these characters into numbers according to this grid. So W is 22 and I is 8. So this is multiplied into 22 and 8. And the AN is 0 and whatever the N is 13. And to multiply this matrix into that matrix, you multiply the row into this column. So 3 times 22 is 66, plus 5 times 8 is 40, and 17 times 8, whatever it is, 156 or something. And okay, whatever. Anybody gives me the results here?
Before modulus or after modulus?
The top one is 104, and the bottom number, I can't remember what it is.
The above is 106.
13.
The above one is 106, and this one is 470.
470.
Yes.
6, I get the remainder, and the remainder should be 2 and 2, which is the letter C twice. And the full thing is CCNI or CCNA. CCNA is a certificate issued in networks. That was just an example of how to use Hill cipher. So the full example, most likely you'll get a question similar to this in an exam setting. So make sure you actually understand. You know how to do this, yeah. Okay, first we start with the 9. The 9 is for the first matrix. We have two matrices. This one has its determinant is 9, and you want to inverse this matrix. In order to inverse this matrix, you need to inverse the determinant first. So to inverse the determinant, there's a way you can do it. You can multiply. It's gonna be an odd number between 1 and 25. So you have to try all these numbers, 1, 3, 7, 9, 15, and all that. And I just wrote the formula. So you take the 9, multiply it into 1 mod 26, and see what is the result. Is it 1? If it is 1, then that's the inverse of 9. If it's not, well, in this case, 9 times 1 is 9, divided by 26, the remainder is 9. It's not 1, then it's not 1. And 9 times 3, well, you know, that's the right one, equals 27. 923 is 27, divided mod 26 equals 1. And 3 is the inverse. Then you can have 9 times. Okay, once you find it, stop. You don't have to obviously go for the rest of it. But I have those in a table, so you can either look at the table to work out quickly and find out which one it is. Just in case you don't remember the table, or you might think it's a different number. Okay, so that's a simple example, and we're finished with that, guys. Any questions?